In this lesson, we shall solve this question in front of us. In the diagram below, ABCD is a cyclic quadrilateral. So we have that ABCD is a cyclic quadrilateral where A is that one, B is that, C is that, and D is that. A, B, and DC are produced. Here's A, B, and DC are produced to meet at E. A, D, and BC. Right, A, D, and BC are produced to meet at F. AFB is 2x. Right, so you have AFB is 2x and DAB is 3x. Right, so that obviously here we have DAB is 3x there, and also the angle AED is x. Right, AED is x. But now, if you look at this triangle, we want to calculate the value of x. So you can look at this triangle here. Let's look at this triangle here. This triangle takes us back to grade 10. Right, takes us back to grade 10 because we know from grade 10 that the angle D1, at grade 10, we have this one is x and that one. So at grade 10, we're taught that if you have a, this one is AB and this is 1, 2, then we have that C1 is angle A plus angle B. And this is exterior angle of triangle is equal to the sum of the interior opposite angles. So C1 is equal to A plus B. So that we have the angle D1 is equal to what? The angle D1 is going to be equal to 3x plus x. And this is 4x. Why is that? Why is that? Right, so which means D1 is 3x plus x. And therefore, if it is 3x plus x, then what are we then able to achieve? 4x. And why is this? From grade 10, it is the exterior angle of triangle. This D1 is the sum of these 3x and that. So we then say exterior angle of triangle. This is how we write it. So we say exterior angle of triangle, and we understand therefore that exterior angle of triangle is the sum of the interior opposite angles. Okay, so yeah, we found this one to be 4x. Then we therefore need to find, right, so we need to find something else. We need to find, right, we need to find the value of x. Right, and so to find the value of x, we continue with our analysis here of this question. And next, we attempt to find D2, the angle D2. So the angle D2, which is this one, is what? Okay, if you are dealing with the angles in this particular triangle, then you have 180 degrees minus the angle D2 is 180 degrees minus these two angles here, which is 180 degrees minus 4x. Okay, so because to get a third angle, you can just say 180 degrees. To get this one, you can just say 180 degrees minus the other two angles. Right, which means therefore angles on a straight line. Angles on a straight line. Right, so that now you have D2, which is D2 is 180 minus 4x. So you have 180 minus 4x. And then now you have the angle B1 is equal to what? The angle B1. Let's look at the angle B1. Right, this angle B1 now can be seen as also an exterior angle of this triangle that goes down like this. So that the angle B1 is 3x plus 2x, which means that it is 5x. So the angle B1 is 3x plus 2x, which is 5x, which is exterior angle of triangle. Right, exterior right, which is the exterior angle of triangle. Right, so that now the angle B1 is equal to the 3x plus 2x, which is 5x. Right, the angle, but the angle B1 is equal to what? This angle B1. This angle B1 is actually equal to the angle D2. Why is this the case? The angle B1 equals the angle D2. Why? Because at grade 11, we're taught that if there is a quad like this, then the exterior angle is equal to the interior opposite, so that in the end, the angle B1 is equal to the angle D2, exterior angle of cyclic quad. Exterior angle of cyclic quad. Right, B1 equals D2, which is exterior angle of cyclic quad. What is the angle B1? It's 5x. We've seen the angle B1 is 5x. What is the angle D2? It's 180 degrees minus 4x. Right, so that in the end, you add the 5x with the 4x, giving us a 9x. And this 9x is equal to 180 degrees. If you divide 180 by 9, this gives us 20 degrees. You see, the question was, what is the value of x? So the value of x equals 20 degrees. So we can therefore say that x equals what? X is equal to 20 degrees there. And we have solved this problem step by step. And therefore, right, so look at this question and make sure you understand our solution, but make sure you actually sort of have the correct sense of what obviously has been done here. But also pay particular attention to the reasons that have been supplied to ensure that you actually understand what's happening. But also, there are many ways to do this question. This is not the only way to do the question. There are like many, multiple ways to do it. Let us look at the next question. Right, the next question is this one. In the diagram, MP is the diameter of a circle. Right, we have that MP is the diameter of the circle. So MP passes through the center of a circle centered at O. MP cuts the chord NR. Right, we have MP cuts the chord NR at T. Here it is. Radius NO and chords PR. Right, so you have the radius NO and chords PR, MN, and MR are drawn. The angle R1 equals 69 degrees. Right, did the examiner show it for us? Well done, examiner. Here is the angle R1. It is equal to 69 degrees. Determine, giving reasons, the size of the angle R2. So we're looking for the angle R2. Where's the question? Where's the question? Who has a suggestion, excuse? What do you think the R2 is? Anyone? Anyone? Senulo, what is the size of the angle R2? What is it? What is the size of the angle R2? So the couple of ways to do the R2, we can start writing it like that, but we can supply a little bit more details. And
it's gonna be 90 minus 6.
Well done, 90 minus 69. Thank you so much, because of this one is the diameter, and this obtains an angle of 90 degrees. So right now we have the angle MRP. The angle MRP equals 90 degrees. And this is an angle in semicircle. Angle in semicircle. So we have MRP Because now it's an angle in semicircle separated by diameter, so you can tell the examiner why this angle is 90 degrees, and then come to that point and then say the angle R2 is therefore equal to, now because the whole angle is 90 degrees, you're just subtracting the 69, so it's 90 degrees minus 69 degrees, and this is actually equal to 21 degrees there. Okay, so that becomes the answer there. So the angle R2 equals exactly 21 degrees there. Okay, so we have got that one. The next thing is we need the angle, the size of the angle. We need the size of the angle O2, O1. What is the size of the angle O1? Who can find the size of the angle O1? Anyone? This one here, what is the size of this angle here? O1. What is the size of this? Who knows? Who wants to try? The angle O1, what is the size of this particular angle O1? Right, so the angle O1 is this one here, but it can be found with so much ease. I know that somebody knows how to do it, and this is all grade 11 work. Who wants to try? Anyone? Anyone home? Okay, we'll remember that. If you have this, okay, so this one here is 69 degrees. So that now we have the angle at center, this one here, which is equal to 2 times angle at circumference. Right, so that this angle here, so the angle O1 is 2 times 69 degrees. 2 times 69 is what? Is 138. Right, yeah, 138. Why is it 138 degrees? Because angle at center is 2 times angle at circumference. Angle at center. Angle at center equals 2 times angle at circumference. Okay, angle at center is 2 times angle at circumference. Like this. Right, obviously we know that this one very well from as early as grade 11 work. And now we want to therefore find the size of, okay, yeah, because of this. So we are able to see, you see the way we are seeing that is as follows. So yeah, this one here, with this here, with this here, like that. Okay, yeah, so that is what we have. Right, so, okay, the size of the angle M1. Who knows M1? What is M1? Because it is this diagram here that has been rotated like that to look that way so that we can be able to find the angle O1, okay? Because it is such that these here are radii, they are actually what you call radii. Each one is a radius. Okay, what is the size of the angle M1? Anyone home? Who knows? M1. Who knows what the size of the angle M1 is? Where is M1? It's this one here. What is the size of this angle here? Anyone? I know that you can do this. What is the size of the angle M1? Anyone home? Quickly, what is the answer? The angle M1. What is it? Right. Who knows? Okay, there's a butterfly here.
Sir.
Ota, yes, please.
Oh, before I had an idea, sir.
You had an idea. Okay, yeah. Well, what were you thinking?
At first, I know that O2
Yes,
plus O is equal to 180 degrees.
yes, yes.
And then since O2 is an exterior angle of
Of the triangle.
MNO, triangle MNO.
Yes. Yes, you can use that. You can use that. Brilliant, brilliant idea. I actually obviously like that so much. And it's a very, very good idea. And it will give us the same answer. Okay, it will give us the same answer. But what we're able to see here, we're able to see a bow tie. We're able to see a bow tie. So that in the end, then, this angle equals this angle. And this angle equals this angle in the bow tie. So what is the angle R2? What is the angle R2? Here. Okay. There are many ways, like the method you're giving is correct. It's going to work. Tando. We know that the angle R2 is 21 degrees. So which means that we can just say also the angle M1 is also 21 degrees. And even if you use the exterior angles and other things, you're going to get 21 degrees. But it's just that this 21 is already there. So you can just say this one is equal to this because they form like a bow tie, you know? And so that you can just say M1 is 21 degrees. And these are angles in the same segment. Angles in the same segment. So, I mean, there are many ways to do it. Angles in the same segment. Okay, yeah, we're just trying to practice geometry. Angles in same segment. Okay, yeah, angles in same segment. Then now we continue. Right, we continue. So angle M2, if it is further given that NO is parallel to PR, right, so angle M2 is which one? This one here. What is the angle M2? Okay, if it is further given that NO is parallel to PR, NO, this one, is parallel to PR. Okay, so we need to find the angle M2. Yeah? Okay. Where's an idea on this one?
Yeah, I might be wrong, but I think M2 is equals to N2.
Okay, that's interesting. Right, you think that M2 is equal to N2? Why would you think, what would the reason be for that? It's interesting. What would the reason be for that?
So the triangle, triangle from what you call this? What you call this triangle that you get when you do the angle at center is equals to 2 times angle at circumference.
Okay, yeah, I hear you. That sounds awesome. That looks marvelous. Let's dissect this together. Let me create a bit more space here. I want us to show the steps a little bit on how to find the size of the angle M2. I remove all this stuff. And we want to find the size of the angle M2. But it helps to just put the other angles like R2, the O1 is 138 degrees. The angle M1 is 21 degrees. M1 is 21 degrees, right? So you can put 21 degrees here. Right, so M1 is 21 degrees. Okay, so right, so M1 is what? It's actually 21 degrees. That's what we got. And we're just interested in finding the size of the angle M2 there. Okay, yeah. Obviously, I mean, you're so much on point there, Cellulo. And obviously, And also the ideas also from both of you guys, they were very, very useful in solving this particular question. We're looking at 8.4, 8.1.4. Okay, now we then have that the angle O2 right, so the angle O2 is equal to what? Right, so the angle O2 here, there are too many ways to do it because you can look at this as a straight line. Or okay. Or you can say, it's easier. So you can say O2 is 42 degrees. The 42 degrees can be obtained in two ways. You can say angle at center is 2 times that one, so that 2 times 21 is 42. Or you can just say this plus this is 180 degrees because this is a straight line. The diameter is a straight line. So that now you can then say the angle O2 is 42 degrees. Angles on a straight line. On a straight line. Angles on a straight line. Okay, so I mean that's something you can have. That's something you can have. So that the angle O2 is 42 degrees. Right, so that now the angle P, right, so that the angle P now becomes of a given size. What is the size of the angle? So in other words, you have obtained that this O2 here is 42 degrees, but or you already have parallel lines here. You already have parallel lines here. So these things here, this is forming a Z, So that now it follows that the angle P is equal to 42 degrees. The angle P equals 42 degrees. And this means that you have alternate angles. Alternate angles, you have NO is parallel to PR. Right, so angle P equals 42 degrees. Okay. Then we have the angle M2. That is what we want. The angle M2, which is this one here. What is the angle M2? Right, so now we have already got the angle P, which is 42 degrees. We've already got that this one is 21. So the angle M2 is obvious. The angle M2 now, because it's the only remaining angle in this triangle here, in the triangle MPR. Because you already know this one, you already know this one, you already know this, you already know, Okay, we want M2, but we know this, we know this, we know that. So we know like 3, like 1, 2, 3. So which means that it's gonna be 180 degrees. Which is 180 degrees minus 180 degrees minus what? 180 degrees, we subtract. Okay, to get M2 now is 180 degrees minus 42 degrees minus 21 degrees minus 69 degrees. And what is the answer? So what is 180 minus this? Which is 48 degrees. Right, if you use a calculator, you'll get 48 degrees. Check this. Right, so that in the end, then M2 is 48 degrees. But why is it that now we have M2 is 180 minus these 3 angles? It means, therefore, you have the sum of angles in triangle. Sum of angles in triangle. Sum of angles in triangle. Okay, where's the question? So now the angle M2 can come here. The angle M2 is equal to 48 degrees. Check this, that if you say 180 degrees minus 42 degrees minus 21 minus 69, you're getting that. Okay, these things, you must repeat them because I want you to master these, but you need to take your time to like learn these things and be in a position to understand them. Be in a position to understand them. Right, so we had 180 degrees minus 42 degrees minus 21 degrees minus 69 degrees. And what is the answer? It's 48. 48 degrees. 48 degrees. 48 degrees. That is the answer. That is the answer. Any question? Okay, where's the question? Who thinks that somewhere we're supposed to do something different? Who thinks that somewhere, somehow, somewhere there is a number that is missing and we need to put the number in? So yeah, who has a question? Where's the question? There's no question. There's no question. There's no question. So we continue in the absence of a question. Right. So the next thing now is to look at this particular question. In the diagram, A, B, C, A, B, C is a triangle. D and E are points on, right, these are points on sides AB and AC. Right. Yes, yes, yes. Who am I talking to? Is it Tumani? Okay, that's fine. Thanks, Tumani. I'm in class. Can I talk to you after 6? Yeah, but you see, I'm in class now. I'm in class now. And I can only be able to call after 6. Yeah. Okay, thanks, dear. Thanks, Tumani. Okay, right. So we are having obviously this situation where you have the triangle ABC, right? And D and E are points. Here is D and E. These are points on sides AB and AC. These D and E are points, respectively, such that DE is parallel to BC. DE is parallel to BC. Use the diagram above to prove the theorem, which states that a line drawn parallel to one side of a triangle divides the other two sides proportionally. So here's the line that is parallel to one side of a triangle, divides the other two sides proportionally. That is proof that AD over DB is equal to AE over EC. Okay, good question. This one is going to teach how to prove this theorem. Sometimes this theorem comes in the exam. Sometimes it doesn't come in the exam. So yeah, stay tuned. What do we do to prove this one? We perform a construction. What kind of construction do we do? Watch this space, because this is awesome news for us. So we're going to actually do what? We're going to perform a construction here, like so. Like this. Okay? So that this one goes up like this. and you have this. And then you have that. So that in the end, then what you're having here is that you have H2, you have H1, and then now you perform a construction like this. And then you perform another construction like this. Right, so like this. So you perform those constructions. How do we therefore describe the kinds of constructions we have done to prove this theorem called the proportionality theorem? We call this one here the proportionality. Right, proportionality theorem. Construction. What we do is we join BE. Join BE and CD. So we have joined BE and also CD. BE and CD have been joined. This one is a theorem, guys, so you need to learn it. It comes in the exams, right? So we're proving this one. And draw. And draw H1 from E perpendicular to AD. Right, so and H2 from D perpendicular to AE. Okay, so what you do here, we perform constructions. You join BE and CD. BE and CD, join them. And draw H1 from E perpendicular to AD. And H2 from D perpendicular to AE. And this is what we do. Next, we present the proof here. Right, to write down the proof, we then say that the following is actually the case. Right, so we then say that this is the proof. Let me write in green that we have now the proof. Right, in presenting the proof, we write it in red. And we then say area. Area triangle, ADE. Area triangle, BDE. Right, so if you look at the triangle ADE, which is half AD. Okay, if you want to find the area of the triangle ADE, what is the area of the triangle ADE? It is half the base. The base is AD. Half the base AD multiplied by the height H1. You divide by, okay, now the triangle BDE is also now here half the base BD multiplied by the height H1. And then now you cancel these things. And then now, which is AD over BD, like this. And then area. Triangle ADE. Area. Triangle DEC. Right, so that in the end then, you have the triangle ADE, which is then now want to find the area of the triangle ADE, but now sticking to this side of the triangle. So we're going to have half AE times the height H2 divided by half EC. Okay, now we are looking at this now, this triangle DEC, so which means half EC times the height of this particular triangle, and the height is what? Is the H2. Obviously, we can see half cancels half, H2 cancels H2. This gives us AE over EC. Okay, so here half cancelled half, and H1 cancelled H1, giving us AD over BD. Right, in the end, then what are we able to achieve here? So that we have the area. Area triangle ADE. Area triangle ADE. So in other words, the area of the triangle ADE is equal to the area of the triangle ADE, because we approach this in different ways. Why is this the case? Because we can be rest assured that this is a common area. This is common. It is common. We are actually establishing and stating the fact that the area of triangle ADE in the numerator is equal to the area of the triangle ADE in the numerator here as well. Now, what about the bases now? We're done with the top here, ADE. What about the bases? We establish that part as well. What do we establish there? We're able to establish that at this point, what we have here, we have the area. Area triangle BDE equals area triangle DEC. And therefore, what we then have here is, okay, the basis. The area of triangle BDE is also equal to the area of triangle DEC. Why are they equal? Because they have the same base. If you look at the triangle BDE, BDE, and the triangle DEC, okay? So they have the same base and height. They have the same base, right? They have the same base and height. They have the same base and height. All right, so that obviously at this point we're able to see that DE is parallel to BC. Right, so we know that the area of triangle BDE, these two triangles have the same base and what? Have the same base and height. Okay, because they lie between the same parallel lines, DE and BC. So now you can choose any base for these triangles. So these triangles, for instance, if you want to choose the base for the triangle, for instance, BDE, you can choose the base DE. In the triangle CED, you can choose the base DE, so that they have the same base, but also because they lie between the same parallel lines, they have the same height. Height is from the base to the highest point. So that now, for example, what is happening here? Okay, you can be able to see that they lie between the same parallel lines, and therefore they have the same height. The height can be drawn, for instance, from a common base to a height. Even here, you can visualize a height here, and then you can visualize the height there, in which case, therefore, they will have the same height there. Okay, good. Next point. We're able to continue and then say, because the tops are equal, the area of triangle ADE is equal to the area of triangle ADE, and the bases are the same. It means hence area triangle ADE, area triangle BDE, area triangle ADE, area triangle DEC. And therefore, in other words, we have taken it from here. We are really saying here at this point, ADE equals ADE in area. Triangle BDE is equal to triangle DEC in area. So that we have this. ADE equals ADE in area, and the area of triangle BDE is called the area of triangle DEC. But what is the area of triangle ADE over the area of triangle BDE? It is AD over BD. So in other words, this one is actually AD over BD. This equals, right, if you look at the triangle ADE over DEC, the area of triangle ADE over DEC, you have AE over EC. AE over EC. And therefore, this is the conclusion. This is the conclusion. This is the conclusion. And now, this is exactly what, because we have to prove that AD over DB is equal to AE over EC, and it is true. It is always that way. Always that way. Always that way. Always that way. So, always that way. Any question? No question, we proceed to the next thing. Right, now the next thing is to prove this one here. In the diagram, M is the center of the circle. M here is the center of the circle. You can see it is a little dot, but this dot is sort of outside and it's not really in contact with the diameter, right? A, B, and C are points on the circle, right? So you have that, you have A, B, and C are points on the circle such that AC equals BC, right? You have AC equals BC. They marked them equal to each other, these AC and BC. Now, PA is the tangent to the circle. PA is the tangent to the circle at A. Right, so in other words, we're able to see that PA, here is PA, P is here, and A is there, and this is a tangent to the circle at A, so we have a tangent there, and then we can be able to see very good things like the tangent theorem. The angle between this tangent and this chord is going to be equal to that angle in the alternate segment over there. Okay, so these are the things that are very important. Okay. Right, so we continue. Right, we continue. We continue. We continue. Right. Right. So now at this point, we continue to analyze these, but yeah, with so much caution. So much caution. Okay. What else do we have? So PA is a tangent to the second at the point A. PQ is drawn parallel to CA. Here is P and here is Q. It is drawn parallel to CA. To meet BA, produce that Q. To meet BA, produce that Q. Now, BC produced meets PQ at R. Right, so there's BC produced meets PQ at the point R. Here's the point R, and AR is drawn. Somebody draws AR there. Let the angle Q be equal to X. Let the angle Q be equal to X, and there is X there. Determine giving reasons 4 other angles, each equal to X. We need 4 angles, each equal to X. Who can find the first angle that is equal to X? What is it? We're looking at 9.2.1. 4 angles, each equal to X. Right, here is the angle X. What other angles are equal to X? Who thinks? Yeah, which one?
A1.
Why?
Angles in the same segment.
And okay, yeah. Thank you so much. Thank you so much. There, you're on point. Okay, right. Obviously, going to write some of the things. Right. So we're able to see that for first things first that this angle is X, but there's this thing here. There's this thing here. This one is parallel to this one, and this thing like this. Okay, so if you have this parallel to this, so that we have A1 here. Right, so that angle A1 is equal to X. Right, so that angle A1 is equal to X. Right. Why is angle A1 equal to X? Because now if these angles in F, they are called corresponding angles. Because you have this and this is parallel to this. Right, because now you have those parallel lines, then you have what you call the corresponding angles, because the angles in F and they're called corresponding. They're called corresponding angles. Right, so we continue. We continue. Why is angle A1 equal to X? Because they are corresponding angles. Okay, look, they are corresponding. They are corresponding angles. Why are they corresponding angles? They're corresponding angles because PQ is parallel to CA. Right, PQ is parallel to CA, and then because of the F here, an angle here, it's equal to an angle there. Okay, but this is one of the angles. So we've got that this one is also X as much as Q is X. What other angles? We need 3 more because there must be 4. 4 other angles each equal to X. We need 3 more. What are the others? Next. Who can find the next angle that is equal to X? Please, guys. The angle B. Well done. The angle B is equal to X. Why is this the case? What is the reason there, Tsenulo?
So I don't know, sir.
Okay. Yeah, because this triangle that is called isosceles, if you have a triangle that this side is equal to this, so this angle is going to be equal to this one in this triangle here. So this one is also X. So because it is in an isosceles triangle like this, if this side is equal to this, then the angles are equal to each other. So which means that the angle B is equal to X. Why is that the case? Angles opposite equal sides. Angles opposite equal sides. Okay, because these sides are equal to each other, and therefore the angles are also equal to each other. Okay, good. So we have that. Next. So we have that angle B equals X. Next, what other angle? We need two more. Two more. What other angles are equal to X? We need two more. Okay, it's obvious now. I even marked some of the angles there. I've already marked something there, and you can be able to see, that one is the third one, because we already have two of them. The examiner said 4. So we need two more. Who can find? Please find it.
So I'm not sure about R2, sir.
R2. Okay. Yeah, R2 is a little bit tricky there. But now there's an angle that I marked here like this, and this angle here, because this one is a tangent. Tangent, and now if we look at the tangent result, so if you have something like this at grade 11, the angle between a tangent to a circle and a chord equals the one in the alternate segment. Right, so that in the end, then, we have that the angle A2 is equal to X. The angle A2 is equal to X. Okay, here is the angle A2. And we're able to see, therefore, that this angle A2, which is here, is an angle between a tangent to a circle and a chord equals the one in the alternate segment. So that you have the angle between a tangent to a circle and a chord equals the one in the alternate segment. So this is the turn chord. Turn chord theorem. Okay, turn chord theorem. Yeah, so that A2 is equal to B. It's equal to, and B is already X, so this A2 is also X as well. So X there, X there, X there, X there. Okay, the examiner is saying 4. There are only 3 we stated. 3 have been stated. So yeah, we need more angles, please. One more angle is missing. The examiner needs 4 of them. They said 4. What is the 4th one? Because you need to get all the marks. But only 1, 2, 3. Where's the 4th one? Sanulo, where is the 4th one? Tando, where is the 4th angle? There's another angle that is equal to X according to the examiner. But which one is it? Which one is it? Please talk to me. It's grade 8, this one. This one is from grade 8. This one is from grade 8. The last one uses results from grade 8 geometry. And both of you guys passed the grade 8 already. So I know very well, therefore, that this should not be a big issue for you. What is the size of the angle? What is the last angle? Because they need 4 of them. There are only 1, 2, 3 we have given. There's another one. Okay, it is not R2 yet. It is not R2 yet, but there's another one that is equal to X. Which one? Hey, you must be able to look at that and say, okay, Mr. Examiner, this is parallel to this. So you have this one here. What do you call these angles that do this thing here? What do you call these angles that do this kind of thing? And now this one is like a Z, because this is parallel to this. So this is like Z. If this angle is X, this one is going to be X. Yes, this is true. This is true. So it means, therefore, the angle P is equal to X, which are alternate angles. Alternate angles because PQ is parallel to CA. PQ is parallel to CA. PQ is parallel to CA. PQ PQ is parallel to CA. Okay. So these are 4 of them. These are 1, 2, 3, 4. And there's a determine giving reasons 4 other angles each equal to x. And we found them. Here they are. Here they are. Next point. Prove that ABPR is a cyclic quadrilateral. Let's look at this one. Okay, looking at ABPR. ABPR is a cyclic quadrilateral. Okay. So now, what do we do here? Okay. Right, so okay. ABPR is a cyclic quadrilateral. So is this a cyclic quadrilateral with a couple of things that we need to take into account? So right, so now, yeah, we need to prove that ABPR is a cyclic quadrilateral. ABPR is a cyclic quad. So, okay, look at this. If this is to be a cyclic quad, what then do we need here? What then do we need to prove here in 9.2.2? We're looking at 9.2.2 right now. And so to prove this, we first note that we already know this is x, for example. And we already know that this angle, we found that a couple of the angles like B was x, but also we found that A2 was x. We found that angle P was x, like this. So, right, so that in the end, we continue with this. Okay, we found that A2 was x, but also the angle A1 was x. Okay, like that. So we found a couple of these angles here, which were 1, 2, 3, 4 of them. So to prove, therefore, that ABPR is a cyclic quadrilateral, you have that the angle B equals the angle P. Right, so the angle B equals the angle P. The angle B equals the angle P. There it is. Because these are like, this is like, they form a bow tie, these things. This thing's like a bow tie. Because you have that this here is this, and this is like a bow tie. And we've already proven that this is X and that is X. So 9.2.2 is just a walk in the park. And we're able to see that the angle B is equal to the angle P. Why? Why is the angle B equal to the angle P? Okay. You say it has been proved. Right, it has been proved in 9.2.1 above. Okay, we're able to establish that the angle B equals the angle P. And therefore, right, because the angle B equals the angle P, this one is X and that is also X. That's why they're equal to each other. Therefore, the conclusion then is that A, B, P, and R are concyclic. Are concyclic. These are concyclic. In other words, these points lie on the circumference of a circle. They're concyclic points on the circumference of a circle. And therefore, we make the following conclusion. AB ABPR is a cyclic quadrilateral. It's a cyclic quadrilateral. Cyclic quadrilateral. Cyclic quadrilateral. Okay, cyclic quadrilateral. And why is it a cyclic quadrilateral? The reason for that, we put it in square parentheses. This is true because of the converse of angles in the same segment. Converse angles in the same segment. Okay, the angles in the same segment result is a very important one, because we first need to have a circle and then the bow tie that we have the angles in the same seg, and this equal to this. Obviously, this is true if you have a circle and 4 points that are concyclic. Concyclic meaning they lie on the circumference of a circle. So therefore, ABPR is a cyclic quadrilateral. Why is it a cyclic quadrilateral? This ABPR, because there's no circle that is visibly passing through A, B, P, and R. There's no circle that is passing through these points. But why is it that we are saying that these points are concyclic? How are they concyclic, these points? Because there's no circle that is passing through these points. These are concyclic because of the converse angles in the same segment result. So if you have angles that look like they are actually angles in the bow tie, then you need to say that you have a cyclic quadrilateral. And this is because the reason is the converse angles in the same segment result. Next point. We need to now do 9.2.3. We need to prove that BA over BQ. Let's do that very attentively. We're looking at 9.2.3 right now. And in 9.2.3, we already know some of the things. Like we already know this one is X, 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 X. And we already know that this is these are concyclic. So if you look at the ABPR, for example, there are too many things we can state here. As a matter of fact, like this angle here is twice X. And therefore, this one is also twice X, like this. Like that. Okay, now look at these and think of these very, very carefully. Right, so yeah. Just look at BA over BQ. BA over BQ. BC over BR. Okay, you already have that this is part of this. Okay, so now if you're supposed to prove this, this is the theorem we just proved, and we've just proven, because it's the proportionality theorem that we've just proven. If you have A, B, C, like this, D, E, you'd have that AD over DB is equal to AE over EC. Why is this the case? It is the case because of your DE is parallel to BC, and this is the proportionality theorem. And this is the proportionality theorem, or you can start, normally this is how we write it. You can just say, you just say the reason, you just say proportionality theorem, why, and then you put a semicolon there, and you then say DE, for instance, is parallel to BC, like that. So that at this point, what we have then is the following. What we then have is the following. What we then have is the following. You have therefore that at this point BA, so look at 9.2.3. Okay, because you already have that this is parallel to that. This is parallel to that. So we have that BA over BQ. Right, BA over BQ is BC. Is BC over BR. Proportionality theorem. Okay, proportionality theorem. Why is it the proportionality theorem here? Proportionality theorem simply because at this point you can see that AC is parallel to QP, like that. So AC is parallel to QP. Okay, but QR is equal to BR. Let's check that. QR is equal to BR. Right. Note that QR is equal to BR because of the base angles. This one is X and that one is X. So this triangle is isosceles. And you can say, obviously now the QR is equal to BR, and the reason is sides opposite equal angles. Sides opposite equal angles. Sides opposite equal angles. So yeah, the QR, the PR, so you can come and compare with this one here. Which means, therefore, you can say, therefore, BA over BQ is equal to BC over, what is the BR? It's QR. It's QR like that. And therefore, this is the answer to this particular problem. This is the answer. So we've been able to establish this. We've been able to prove that BA over BQ is BC over QR. And then we have proven this result. Any question? Who has a question about this one? Who is confused? A different suggestion. A different suggestion. In the absence of a suggestion, we look at the next question. We look at the next problem. Okay, let's just look at this one very quickly. In the diagram, TSR is the diameter. TSR is the diameter of the largest circle. TSR is the diameter of the largest circle, having center S. So S is the center. So you have that ST is the radius, and also SR is the radius. Chord TQ of the largest circle cuts the smaller circle at M. There's chord TQ and cut the smaller circle at the point M, and here is T and here is Q, and all these are visible. Okay, right, so we continue to solve this, but you're in detail. Let us look at what information has been provided up here. Right, and cut the smaller circle at M. Okay, here's the M, we've seen that. PQ is a common tangent. PQ is a common tangent, in other words, to the two circles at the point Q, or at Q. So in other words, we have that the PQ is a tangent to the smaller circle, but it's also a tangent to the bigger circle there. Okay, good. Let us continue now and analyze these, but analyze these very carefully. So prove, okay, now we have that before that, they said that SQ is drawn. Okay, here is SQ, which has just been drawn. RP is perpendicular to PQ. Right, so we have that RP is perpendicular to PQ. Okay, it's making an angle of 90 degrees. Okay, here's the 90 degrees there. And MS is parallel to QR. Right, MS is parallel to QR. Parallel lines there. Parallel lines there. Okay. proof giving reasons that SQ is the diameter of the smaller circle. You need to prove that here is S and here is Q. Prove that SQ is the diameter of the smaller circle. Okay, very, very straightforward. Who can suggest the proof? How would that be proven? How would that be proven? What is the proof of that one? How does the proof go about that one? Okay, but obviously because we know that TSR is the diameter of the larger circle, so it means that this angle is 90 degrees. So that the angle Q1 plus the angle Q2 is equal to 90 degrees. Okay? Yeah, 90 degrees. Is equal to 90 degrees. And this is an angle in semicircle. Angle in semicircle. Angle in semicircle. Right, the angle Q1 plus Q2 is 90 degrees. Angle in semicircle. So yeah, because this Q1 and Q2, they are angles that are subtended by the diameter theory. So this is an angle in semicircle, where semi means half. We're dealing with half a circle. The angle M2 is 90 degrees. The angle M2 is 90 degrees. We state that one. The angle M2 is equal to 90 degrees. Why is this the case? The angle M2 is 90 degrees, and this means that you have the co-interior. Co-interior angle. The angle M2 is 90 degrees because now this one is already parallel to this. At grade 10, you were taught that if you have two parallel lines, an angle that is here and an angle that is here are co-interior. So if you take the dot plus the asterisk, you get 180 degrees. Okay, so at this point, this one is already 90. That must be 90, so that if you add them together, you get 180 degrees. And this is true because of what you call the co-interior angles. Right, so these are, so in other words, or you can say the M2 is 90 degrees because it's a co-interior angle. And it's a co-interior angle because MS is parallel to QR. Parallel to QR, like so. Okay, and this is what we have. Moreover, so we have that M2 is actually 90 degrees there. Okay, but now it means therefore this SQ here subtends an angle of 90 degrees, the circumference of the circle. Therefore, good students, SQ is a diameter. Is a diameter. So we have been able to show that this SQ is the diameter because it subtends an angle of how many degrees? Of 90 degrees at the circumference of the circle. Subtends an angle of 90 degrees at the circumference of the circle there. So we continue to solve these particular problems. Right, what's the question about this? So obviously we have just done 10.1.1 that said proof giving reasons that SQ is the diameter of the smaller circle. We've shown that this SQ is the diameter of the smaller circle because SQ subtends an angle of 90 degrees at the circumference of the smaller circle there. Next, we need to prove the 10.1.2. We need to prove that RT is equal to RQ squared over RP. We need to prove this one. How do we prove this? But also, how do we start? We set the scene as follows. Right, we start by looking at the question to be solved, 10.1.2, and we attempt to establish a proof of this by looking at a couple of things. Right, so we need to establish that this is true, and this uses what you call the triangles that we need to establish. So we need to first play around with this. So to play around with this, we can perform some division here. So we can look at these as RT is equal to This RQ squared, you can write it as RQ. Okay, let me write a bit clearly here. I need to sort of break these down because to prove these things in geometry, you need to actually be in a position to find the triangles in which to prove similarity. Right, so we need to say RT is RQ times RQ. RQ times, and then here you have RP. So that now we have RT over RQ. Right, and then we have RQ over RP. Okay, so you can cross multiply these things. Like now you then cross multiply and multiply RQ times RQ, and you get RQ squared. All right, so it's we continue then to we continue to look at the 10.1.2. All right, now to look at the 10.1.2, you need to look at a couple of things. What do? We have seen, therefore, that if you look at the RT, let me look at that again, over RQ, which is RQ over RP. Okay, we saw that. But what triangles does it? So you look at RT. Here is R, there, and here is T. So we're looking at RT, and then you are looking at RQ as well. Here's RQ. And then now, obviously, you have the RQ here. So now this RT, RQ appears to describe a triangle, and we're just going to obviously state that one explicitly. But also there is RQ and also the RP. Yeah, so it describes also the triangle RQP there. So to do this question, to prove this one, we're going to tell the examiner, and this is how we write the answer in the exam. So in triangle RTQ, in triangle RQP, we note that the angle T is equal to what? The angle T equals the angle Q3. Right, the angle T equals the angle what? It's equals the angle Q3. Right? And this is what we call the 10-chord theorem. 10-chord theorem. Right, so Q3 is equal to T, and this is the 10-chord theorem. Okay, 10-chord theorem. So yeah, look at this and think about it. And think about it. And think about it. And think about it. So the angle T is equal to Q3. The angle T is equal to Q3. So yeah, it's 10-chord theorem from grade 11. Okay, next. Next point. We have that the angle Q1 plus Q2. Right, the angle Q1 plus Q2 here is 90 degrees. Why? Why is the angle Q1 plus Q2 equal to 90 degrees? Okay, because it's an angle in semicircle. Angle in semicircle. Angle in semicircle, that is 90 degrees there. Angle separated by diameter. Moreover, we have that angle Q1 and Q2 added together, they give 90 degrees, but also this angle P is equal to 90 degrees. So we note, therefore, that therefore the angle Q1 plus the angle Q2, let's just write here. Let us write here. Right, so the angle Q1 plus the angle Q2 is equals to angle P, which equals 90 degrees. Okay, yeah, so you have that this is 90 degrees. Okay, we have that this is also 90 degrees and this is 90 degrees. So this angle here, okay, remember that to prove similarity of triangles in these triangles, you must prove three things. So this is one angle. And then now this one is the second thing. Second, okay, so you take an angle in the triangle RTQ is equals to the angle there. But you need three of them. So we've taken that angle T is equal to the angle Q3, but also this one, 90 degrees, is also 90 degrees in the triangle RQP, RQP, triangle RQP. Right, okay. Okay, yeah. So we continue. Third angle, the last one. Okay, but why is this the case? Right, so therefore, obviously, Q1 plus Q2 is angle P equals to 90 degrees over there. The angle, now, this one, the triangle RTQ has R1, and the triangle RQP has R2. So because we already have two pairs of angles that are equal, then it means the remaining angles here in the triangle RTQ in triangle RQP, R1 equals R2. Why is this the case? Angles of triangle. Angles of triangle. Okay. Angles of triangle. Right, therefore, the triangle RTQ is similar to triangle RQP. Okay, RTQ is similar to triangle RQP. Why? Why is this the case? Because we have 1, 2, 3 angles respectively equal. So angle, 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 like this. Now, because of the angle, angle, angle property, we can do that in green color. And we can take the first two and the second two like these. Because these two triangles are similar, then we can say RT over RQ is equal. So RT over RQ, then we have TQ over QP. And this is equal to, you can take the first and the last. RQ over RP. Right, like this. So that then in the end, you take this one and this one, because you must get, according to this, you must have RQ squared. You will need RQ squared, so that to get RQ squared, then you need to cross multiply this with this. So in other words, this is going to produce exactly RT over RQ is RQ over RP. RQ squared. Or if you cross multiply this, RQ times RQ is RQ squared. So it means, therefore, you have RT is equal to RQ squared over RP, like this. So RT is equal to RQ squared over RP. So yeah, that is the proof to 10.1.2. We have proven this one. We have to prove that RT is equal to RQ squared over RP, and we've just done that. So yeah, just follow this. I'm going to send you homework on the WhatsApp group. So yeah, you need to make sure that you try more and more of these problems. But next thing that you're going to do is to do 10.2. 10.2, if ms is 14 units, right? So you have ms is 14 units, and pq is the square root of 640. PQ is the square root of 640 units. Calculate giving reasons. The length of the radius of the larger circle. We want the radius of the larger circle. Here's the larger circle. We want the length of the radius, the distance from the center to the circumference, like TS or SR or SQ, etc. We want to find those. Let's look at that. 10.1.2. Okay, now let's look at the fact that MS is 14 units. And PQ is the square root of 640. Like that. So we have that 14 units for MS, and PQ is the square root of 640. Calculate giving reasons the length of the radius of the larger circle. Okay, so yeah, we have that. We have that. So in the end, then, we have 10.2. Right, so let us find the length of radius of the circle, like TS or SR, okay? Or SQ. Any distance from the center circumference will suffice to be found there. Let us proceed to find this one, as a matter of fact. Now, but to find these, there are a couple of things that we obviously need to consider. First things first, we need to find we need to note the result that we're going to use. Recall that. So we recall that now to use this, we want to find the radius of the larger circle. So the radius of the larger circle, first things first, is actually nothing other than what? Right, if you look at, for instance, what we have is RT. We can find RT first, because RT is the diameter, so that RT is equal to RQ squared. RQ squared divided by RP. Divided by RP. Right, so we continue. We continue. So that now in the end, then, what then we have is as follows. So if you have we just need to find the RQ, because we already know this one from the previous result. But now we want to find the radius of the larger circle. What do we do? We proceed as follows. We need to find QR or RQ. What is RQ? Right, RQ, what is it at this point? Okay, because this one from grade 10. At grade 10, we're taught what we call the midpoint theorem. Midpoint theorem. What is the midpoint theorem? The midpoint theorem tells us that if you have the midpoint like this, and if this one is A, B, C, D, E, then the length of DE, is half BC. Is half BC. Or you can come and say BC, if you cross multiply here, BC is equal to 2 times DE. Okay, that allows us to find RQ here, so that RQ from this can be found, because you already know this one is 14 and this is a radius. So this is equal to this. So you have sort of that S is the midpoint, but also because this is parallel to this, so you have the midpoint theorem applying there. So that in the end, this RQ is 28. It's 2 times 14, which is 28 units. Right, because it is longer than this one, and using the midpoint theorem from grade 10, so that in the end, 2 times 14 is 28 units. And we have that this one is 28 units. And the reason for the 28 units, to tell the examiner that it is the midpoint theorem. Midpoint theorem. Midpoint theorem. So that we have RP squared. So that we have RP squared. Okay, so this one you already know is 28. These are Q. And then now this one you already know is 640. So we can use Pythagoras here. We can use Pythagoras because it's a triangle now. We already have these here. What does Pythagoras? So we can use Pythagoras to find RP squared. So we square the hypotenuse and we minus the other side. So we have 28 squared, but we minus the square root of 640. And we square these. And therefore, the result is equal to, if you subtract everything, is 144. So that RP is the square root of 144, which is equal to 12 units. Which is equal to 12 units. Okay, yeah, so you have 12 units. Okay, so if you have the RP now is 12 units, and the RQ is 28, the conclusion, therefore, is therefore as follows. We therefore need to find RT. So then we have RT is equal to RQ squared over RP. Over RP. It is this one, this formula here. But what is RQ? It's 28 squared over. What is RP? It is 12. Okay, so if you simplify, it's 196 out of 3. 196 out of 3. And then now, we need to remember that it is RT. And this RT is a what? RT is a diameter, because from R to T we have a diameter, and therefore we just need the radius. So we need half of RT, right? So in other words, we can then say that is the radius. So we can take anything, right? So the radius of the largest circle, you can call it, for instance, because we are dealing with RT as a diameter, take anything, any radius, like you can take TS or SR. Let's take RS. Right, RS is half RT. Okay, RS is a radius, is half RT, which is half of this. So if half of 196 out of 3, 196 out of 3 is exactly 98 out of 3. So yeah, and this is the answer, because if you divide 196 by 2, you get 98. And this is 98 out of 3. So it means, therefore, it is 98 units. It's 98 units. So yeah, that is the answer. It is exactly 98 units there. 98 units there. Where's the question so far? Any question? Any contribution? Any idea? Right, I think that we've done much for now. We're going to meet again at 8 p.m., right? So yeah, we started at 4 p.m. on average, just a few minutes after. Yeah, so we're good.